I would now like to introduce Eddy B. Brixen, audio specialist at DPA Microphones. Eddy has been working with DPA for 12 years, mainly on R&D and application activities. Eddy is also a consultant and the owner of EBB Consult in Denmark, where he advises on broadcast techniques, electroacoustic design, and other audio-related topics. He is also a lecturer at many well-known higher education institutions in Denmark and an established textbook author in the area of electroacoustics. Eddy is a member of many audio-related organizations, including the Audio Engineering Society, where he is currently chair of the Technical Committee on Microphones and Applications. And with that, I would like to give the mic over to Eddy.
Hi everybody, and welcome to this webinar. We're going to talk a lot about recording the voice, or mostly about what the voice is like and how the sound field is around the head and around the body. And we are going to talk about speech intelligibility, and hopefully everybody will get something useful and some useful knowledge about the topic. So I will just outline the headlines here for this webinar. We'll start up with speech, the voice as a sound source. Look at that. Then we will look at the sound field around the human body, at least the top of the body. And we will talk about speech intelligibility, talking about placing the microphone, and then there will be some conclusions in the end. So let's start with the speech, the voice as a sound source. We will talk about the human voice. We will talk about waveform, pitch, frequency range, level. If we look at the cut through of a body here, we will see that we have some lungs that will produce some air that passes the vocal cords. And we have the pharyngeal cavity, nasal and oral cavities in the head that will form and shape the sound of that, the sound produced by the vocal cords. And then we can use our tongue and we can use our lips, and we can form all this together in language and singing and so on. But when we look at the voice as a kind of sound source, it's a little peculiar, because where does it start? Where is the 0 point of the source as such? If we look at the acoustic center of the voice and as a function of frequency, we can see here that around 800 Hertz, it looks like as if the voice starts a little outside the mouth in front of the lip plane. And we have all the other frequencies, they will just seem like they are starting behind the lip plane. So we don't have a perfect point source as the voice, but as something else, which gives us sometimes a little problem. When we change the distance of a microphone, we may change the spectrum of the speech that we actually record. When we look at the waveform, here is 3 words. You can hear it like this.
6, 7, 8.
It's typical here that you have some voice sounds that are generated by the voice cords, but you also have some noise sounds, 6, 7, 8. And these noises are added to the vowels, and that form a kind of language. At least at the Western languages, it is like that. When we look at this waveform, which we try to record, we can see that we have here a RMS, average level, or RMS level, which is minus 17.3 dBFS relative to full scale. However, the peak level is minus 0.4 dBFS. That means there's a huge difference between the peak levels and the RMS levels. The RMS levels is very often what we read on the level meters, but the peaks is actually what we want to record to make the full speech without any clipping occurring. So we have to take care of that. Whenever there is a recording, we have to make the space for it all. If we look at the pitch of the voice, or F0 as it may be called, we can see here is a scale, and we can see the range of singers from bass to soprano, and along with that we have the keyboard of a piano. If we look at the same thing here, we have the upper lines here indicating the singers. Then we have the speaking voice, which actually is something in between. Lowest are the male voices, around 120-30 hertz or something like that as an average. And female voices around 1 octave higher, and then children's voices around 300 hertz or something in that range. So what characterizes the voice is actually also the pitch of the person talking. Talking about the level, actually we may have different levels in our voice depending on the vocal efforts. If you whisper, there's no voice used, just very often only the air passing the cavities. And then we have casual voice, which is very low and normal and loud and shouting. And we will have different levels depending on the vocal effort. Actually, we'll also very often change the pitch. So if we shout, we will do it with a higher pitch than we would do if we were just talking normally. In around 1 meter's distance, the sound pressure level is something like 60 decibels, and that's a kind of reference for us. It's a linear level that's around 60 decibels. If we look at the spectra of the voice at different vocal efforts, we can see that the frequency of the females on the left side, and we can see a casual voice. There is the maximum in the low end of the spectrum, but when the voice is shouting, it's a shouted voice, then the maximum is in the middle of the frequency range. So the spectrum changes also with vocal effort, and that's why we are able to detect what kind of effort that a person may use, and that's not depending on the reproduced level of the same utterance. On the right side, we have the males, and it's something like the same we see here. What's important here is for non-tonal languages is that the range of consonants, which are important for the speech intelligibility, is actually in the right side of each spectrum. And that's very important. If that will not survive, we have a lack of speech intelligibility. The level of voice, well, how loud can it get? This lady here can produce 152.4 decibels peak at the lip plane. She was a part of the DPA development of the de facto microphone, where we wanted to see how loud does it get when it gets loud. And this is really loud, I can tell you. Okay, we'll leave this and move on to the sound field around the human body. And we'll see what the directivity of the human voice is, sound field on the chest and around the head. First, the directivity. Here we have two polar plots. On the left-hand side, we have the A-weighted sound pressure level of a person. It's a horizontal plane, and moving around this person and using a sound level meter, we would measure something like this if it was normalized on axis in the 0 degrees right this way. But that's not the full story, because if we look into different frequencies, we can see that the directivity actually changes. The red curves here are the lower frequencies, and the more blue we get, the higher frequencies we have. And we can see at higher frequencies, we get further directivity. We really have a directive voice at higher frequencies. If we move to the vertical plane, again on the left hand side, we have the A-weighted Sound pressure level, A-weighted, means that lower frequencies doesn't count so much in this, and the frequencies around 1 to 2 kilohertz, they count a little extra. But you can see here we have a figure, polar plot, that tells us that there is a little more sound in this angle in front of the chest of a person. Somebody may say, well, that's because of the chest talking, and I have to say the chest does not talk, but the chest reflects the sound. So stop talking about chest talking. It doesn't. It's the voice reflected on the chest. If we move to the right side, we can see the same thing as we saw before. At the rear of the head, the low frequencies can be heard, but the high frequencies are not good. So that's why we have to be in front of a person, for instance, to get the right intelligibility of that voice. And again, we can see what kind of frequencies that are reflected off the chest and gives these bumps on the polar plot in the vertical plane. I can tell you about an experiment that was carried out some years ago. It was made in an anechoic chamber, a microphone positioned 1 meter from a person, and then different microphones could be placed on the person's chest or head to see what is actually the difference. The spectrum of the voice is of course not a straight line, but we use this as a reference. At 1 meter's distance, this could be a reference because that's what we normally hear when we talk to people standing in front of them. At a 1 meter distance, that would be quite normal. So this could be a kind of reference. And now we, from this experiment, where we have this reference microphone in 1 meter's distance, we put a microphone on the forehead of that person. And then we have a curve then that expresses what is the difference from the straight curve. What is the difference of the spectrum? How is it affected by this new position here? Actually, this is a quite flat position compared to other positions. It's very often used in musicals and on stage because you have a fairly flat. And the closer you get to the nose, actually, the flatter it gets. But it doesn't look very nice on stage if it's just above the nose. But on the forehead, at the hairline, it could be looking something like this. Of course, it's louder, but we'll come back to that a little later. So now we take the next position. That will be at the ear in this case. And at the ear, we have this roll-off at higher frequencies. Of course, it's louder than at 1 meter distance, but the frequency here is changed, and we have taken something out of the intelligibility, and we have to compensate for that in one way or another. A third position here is a cheek. Now it moves to the corner of your smile, and again you can see there's a roll off. It's not as much as it was at the ear, it's less than that, but still you have a frequency response that is a little different from the 1 meter distance. And another position here is actually on the chest. So what happens here when you put it on the chest? Well, one thing here, you'll have a dip of up to 10 dB in the range of 2 to 4 kilohertz when you put this microphone here. What we have not mentioned yet is the bump around 800 hertz, which they all have, and this is it stems from the size of the head, actually. So if we take a look at all these positions here and look at the curves, all of them, we can see at the forehead we have this 800 hertz bump, and we have almost a straight line. It's a little, of course, not quite straight, but it works quite well. And if we move on to the ear position, you can see the bump and then a roll off here. And moving to the cheek, again the 800 hertz and a roll-off that not as much as at what we found at the ear. And finally, we have the chest, 800 hertz, and this specific cutout at 1, 2, 3, 4 kilohertz in that range. And that's really annoying because that's where we find the frequencies which we'll later see that are important for speech intelligibility. So that's not a optimum position if we are not correcting it in one way or another. I can just try to demonstrate what it's like. We switch to this microphone I have in my hand, and I can place it at the chest. It's down here, closer to the chin, and I can move it on the side and can move it on top of my head, and I guess that you can hear some differences depending on where I put the microphone. So that's very important, and this is what these curves illustrate. How much is it actually that it changes the spectrum when you change the position of the microphone. I said I would come back to the level, and you can see here these are the levels compared to what we get in 1 meter. If we put the microphone at the forehead, we will have something like 14 dB more level compared to what we had in 1 meter's distance. But you can see out of all this that the cheek, the blue one here in the middle, actually you get almost 10 dB more than you would have from a position, for instance, on the chest or on the forehead. There's really a lot to get from having the microphone, as I have right now on my cheek. So that's very important. If you want to reduce the gain of your microphone, this could be a position to place it. So after having seen the effect of the sound field around the head, we'll move to some information about speech intelligibility. So we'll go through some dynamic range of hearing, and actually that's of our audience, we could say. And we'll talk about frequency spectrum versus importance regarding intelligibility, and we'll look at some signal to noise ratio when we talk speech in noise or speech in background sounds. Here's what we could call the dynamic range of the hearing. At the very top on the right side we have the limits where it begins to hurt us if it gets louder. The bottom is the threshold of hearing. If the sound is softer than that, we will not be able to hear it. When it's above, we're just able to hear the thing. And speech is just right in the middle of this sensational area, and that goes for normal hearing. If we look at the right side, we have a curve for elderly people. As you get older, you will feel and find that the threshold of hearing will change. There will be a change of that, and it moves upwards. And the problem here is that the important frequency range, which is marked on the left side, if we look at that in the right-hand curve, we can see that we get difficulties of understanding words in that case. Looking into the importance of the spectrum, you can see that the upper curves, the columns here, show the typical level within octave bands of typical speech, average speech, something like that. And you can see around 250 hertz, we have the highest level of the column. But if we look at the curve below, the columns below, the blue ones, then we can see that the most important regarding speech intelligibility, that's the 2K, the 2 kilohertz octave band. That's the most important here. And let's hear what's important in speech intelligibility. Here, two curves, they show what is the intelligibility as a function of a high pass filter or a low pass filter. We'll start with a low pass filter, and you'll hear some voice here, some speech, and at first there's no cut off, so it's straight the sound as it was recorded. And then comes a low pass filter that is set at 8 kilohertz and 4 kilohertz and 2 and so forth. And we will listen to how the speech intelligibility gets less and less as we approach the lower frequencies.
In language, infinitely many words can be written with a small set of letters. In arithmetic, infinitely many numbers can be composed from just a few digits with the help of the symbol 0, the principle of position, and the concept of base. Pure systems with base 5 and 6 are said to be very rare, but base 20 occurs in English when we use score, as in 7. Eventually, no system could keep pace with the decimal or Arabic number system, which has 10 numerals. The digits 0, 1, 2, 3, 4.
All right, I guess you can hear that the intelligibility was reduced as the higher frequencies were cut off, or we use this low pass filter. We'll move on to a high pass filter. So we start with the filter in the low end, and then everything is still there above the cutoff frequency. So we'll start here at 100. We'll start here at with a flat response.
5, 6, 7, 8, 9, and a decimal point. The numerals take different place values depending on position. So the number 819.65 can be shown as 8 times 10 to the 2 plus 1 times 10 to the 1 plus 9 times 10 to the 0 plus 6 times 10 to the minus 1 plus 5 times 10 to the minus 2. Monetary systems have evolved to make use of this base 10 notation. France became the first decimal country in Europe in 1799, joined by Belgium, Italy, and Switzerland in 1865. Germany's decision followed 8 years later, and the Scandinavian states and Russia changed in 1875.
Well, I guess you were able to hear that. You could still understand some of the words, even though a lot of the low frequency content was cut off. And that's why the high frequencies are very important, especially in non-tonal languages. When we talk about speech in noise, in this context, noise, it could be any kind of real sound in the back or music or whatever. We know that the level affects intelligibility. If we have a signal to noise ratio that is negative, it means that there's, in this case, 10 dB more noise or background sound, which actually becomes foreground sound, then we have a reduced speech intelligibility. In this case, it will be at a maximum of 70%. But the thing is, having a minus 10 dB signal to noise ratio, still it is like that. When people perceive and receive the sound around 60 decibels, then it's the optimum. The ear is tuned for 60 decibels because that's a normal speech level, and the maximum intelligibility exists when it is received at 60 decibel. And still, when it gets higher, still around 60 decibels, we have highest speech intelligibility. So it does not always help to shout. Of course, if it improves signal to noise ratio, it's an advantage, but else it doesn't. So another thing here is if you suffer from dyslexia, it makes speech and noise even less intelligible. It's worth knowing when you mix for different kind of program materials. Now we'll move to placing the microphone, just to discuss what is possible here and what you should consider when you put it on the chest or on the head. First, have you ever heard this? Well, 2 TV anchors as they sound like. Well, I don't know how many that have their ears on the chests of these persons. Some may have, but not all. So that's not the position. You would never put a camera there, as I just did in this case. But normally you wouldn't do that. But here we put the microphone. That's a strange thing. But we are not used to hear the voice from this position unless we pick it up with our microphone. So we have some considerations to make when we are placing the microphone. Meaning, just don't attach it. The sound is depending on the microphone position, as we have seen. It really matters where you put your microphone, and you have to think of it, where is the optimum for your recording you're going to do. You should avoid shadowed positions if possible. Of course, if you make film and you want to hide the microphone, you should consider to pick a microphone that has a boost to overcome the reduction of the high frequencies in clothing and stuff like that. But else you should avoid shadowed positions. And then remember that the SPL at the cheek is approximately 10 dB higher than it is on the chest. So if you want to improve your signal to noise ratio and have less background noise and have less gain on your microphone, that's a perfect place to put the microphone actually. So placing the microphone on the head provides stable SPL despite movements, because when you move your head from side to side, the microphone stays in the same position compared to the mouth. And remember to equalize the sound when the microphone is in an odd position, because the sound will change in each position that you choose for your microphone. And you have to listen. One major problem here is that if you heard it for some minutes, you have made a kind of white balance on the sound. You think it sounds all right because you get used to the sound. But come with fresh ears and listen to the voice you have recorded, and just assess, evaluate if that sound is right, and make your equalizations. You may get trained to make the right equalizations when you are used to place the microphone in different positions. And then of course you should keep clear of pop noise, meaning the P's sound and stuff like that. Get rid of that if possible. And you really should have the final signal to noise ratio in mind. If you record in the studio, you can have a very high dynamic range, but sometimes when you finally present it to people, there may be some music, real sound or anything, background noise, that reduces the possibility of understanding the sound coming out. And then you should create headroom for your recording and not headache, I should say. Some conclusions. We've heard about speech, the voice as a sound source, the sound field around the human body, speech intelligibility, placing the microphone, and now is the time for questions, and hopefully we have some answers to that. Thank you.